we continue to look at the envelope of a one parameter family of curves. In the last video, we looked at the straight line. Alright, we're going to look at the quadratic curves right now. But since it's one parameter family of curves we're dealing with, you'll find that the straight line, the quadratic curve and the straight line, they don't yield an envelope that follows the strict definition of an envelope. Right? In a later video, we'll look at an example that you're more likely to get in an exam, like a final exam. The straight line and the quadratic, you're not likely to get those, but in that example, in a later video, you're likely to get that one. But let's look at this thing here. Suppose you have y is equal to ax squared plus 2x plus 3. This is a quadratic function where a is a parameter. Alright? Remember, the parameter can be represented by any letter. We could use p, but let's use a for now. Remember what to do. I have the steps written here, the major steps. You rewrite and say equals 0. So we have ax squared plus 2x plus 3 minus y equals 0. Alright? Then differentiate partially with respect to the parameter. So when you differentiate partially with respect to the parameter, now remember this is ax squared. It might look confusing because you are accustomed to saying dy by dx, and then you would multiply this by 2 and reduce the power by 1. But in this case, x is a constant. So you have to be careful. So let's rewrite this as a to the power of 1 x squared, a constant, plus 2x plus 3 minus y equals 0. Everything here is a constant, alright? Each of them is a constant. So when you differentiate and say delta of the function by delta a is equal to, it's 1 times a to the 1 minus 1 times x squared plus, when you differentiate the constant, you get 0 plus constant 0 plus constant 0. All of this will be equal to the derivative of 0, which is 0, right? So what you have here is 1 a to the 0 times x squared. So that will give you a to the 0 is 1 times 1 times x squared, which is just, it all boils down to x squared. Alright, equals 0. So, what this seems to be saying is that x equals 0. Alright? So here, the envelope is when you substitute, you solve simultaneously. In this case, you use substitution method, x equals 0, so y is equal to a times 0 squared plus 2 times 0 plus 3. So what it all boils down to is that y equals 3 is the envelope. Now let us look at this function y equals ax squared plus 2x plus 3 graphically. Alright, this is our graph, but we still have these things from our previous work. Let's erase these graphs. Alright, get rid of these graphs. Alright, so what did we have again? Y equals ax squared plus 2x plus 3. So our first graph, y equals 1x to the power of 2 plus 2x plus 3. Let me just copy, Control C, so that I can paste it later on. So this is one graph. Let me paste, Control V, and change this to 2x squared. Then we paste again, Control V, and change this to 3x squared. Then we use 4x squared. Alright, so let's look at this. Let's zoom in and see what's going on here. I just thicken all of these lines. Alright. Make them thick. All of these curves are. Alright, so here now. These are the family of curves, alright? The various curves that we have. Now, what was the envelope? The envelope is y equals 3. So we put in y equals 3, and this is the envelope that we have here. Y equals 3. So you see, this is not a traditional type of envelope, right? It actually is a locus. It cuts the curve, but there's a meeting point right here at 3. Alright? All of them meet at 3. Alright. Now, let us make a little change to this. Let us use the B part as our envelope. Alright? So let's erase the work that we did down here. We say y is equal to x squared plus bx plus 3. So we write it, we're finding the envelope, we write it as x squared plus bx plus 3 minus y equals 0. Alright? Now, the partial derivative with respect to the parameter b is going to be x. See that? Because we consider this is a constant, so it's 0. This is a constant, this is a constant. These will go to 0. But b to the 1, x, so it's going to be, you bring down the 1, just being careful here, right? It's going to be 1, b to the 1 minus 1, but 1 minus 1 is 0. And then b to the 0 is 1. So it's 1 times 1 times x, so it is x. So x equal, when you differentiate 0, you get 0, alright? X equals 0. So again, y equals 3. When you substitute 0 and 0 plus 3. X squared plus bx plus 3. Let's see how that will go. Let's just modify these. X squared plus 1x plus 3. Alright. This, I don't want to mix them up, you know. Alright. Let's erase them. Alright. Let's delete them and start over. I don't want them to get mixed up. So we have x squared plus x plus 3. Okay, good. Let's make this thick and have some color in it. Then we have x squared plus 2x plus 3. Nice. Let's change the color of this and make it thick as well. Then we have x squared plus 3x plus 3. Okay, so this is what is going on. So after that, we have x squared plus 4x plus 3. Because remember that we can change the thing there, the parameter for various graphs. So this is what we have. And then we still have our same envelope, y equals 3. Alright? So this envelope is where this line touches all of them. So the main point is that the envelope must touch all of them. Alright? Alright. Let's do one more thing now. Let's make the end part here the parameter. Let's just erase what we have here and try a little thing here with this. So what we're going to have is x squared plus, let's say 2x plus c, where c is the parameter. Now, how do we find the envelope again? We write the function as a function of the variables x, y, the parameter, and any constants equals 0. So we have x squared plus 2x plus c minus y equals 0. Then we differentiate with respect to the parameter, whatever it is. In this case, it is c. If we differentiate with respect to c, what do we get? We get 1 equal, and then we differentiate the 0 part, we get 0. But hold on. This is a contradiction. 1 and 0 cannot be the same thing. So you can say this family of curves, they don't have an envelope. We're going to plot them. They're not supposed to have a common point where they are touched, or where you can draw a curve to touch them. So let's see. X squared plus 2x plus c. Let's just change them now. This blue one is x squared plus 2x plus, let's start at 1, plus 1. Okay. The red, x squared plus 2x plus 2. Alright. The green, x squared plus 2x plus 3. The light blue, x squared plus 3x plus 3. X squared plus 2x plus 3. It's 2x I should have. What was it again? X squared plus 2x plus 4. Was it that it? Alright. Interesting. Suppose I have x squared plus 2x plus 5, and then x squared plus 2x plus 6. I'm going on and down like that. Let me change up this to some other color here and make it thick. And then change up this to some other color here and make it thick so we can see it. Alright, So as we can see, there is no specific point where they come together. They never come together. Alright? So here we can say that these curves they don't have any particular meeting point. They don't have an envelope, right? These curves don't have an envelope. There's nowhere that they actually meet, and you cannot draw a line where that is tangential to all of them, right? Now here, suppose you do this now, plus x squared plus 2x. Alright, let's use this one. X squared plus 2x plus 1. Alright, and you have x squared plus 2x plus 2. But in this case, we use 3x and x squared plus 4x plus 4. Alright, so the only way to make them move away is to change two parameters. And if you make this 2x squared plus 4x plus 4, right, we have this situation. Alright, anyway, as I said before, you probably wouldn't get these type of curves in an exam. It's going to be another type, which we'll look at in our next video. So I'll see you then.